Hello students, welcome back to the JEE Last Mile Preparation Series 7. Today we will take up questions 13 and 14. But before I do that, by now you already know that I am Sujata from CBSE NEET JEE Chemistry.in, and we are bringing you 2 questions every day until April 4th to help students get that extra edge for their JEE Chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is given in the description below. Let's get started. We are in the second chapter of physical chemistry, atomic structure or structure of atom. Again, it is a conceptual and numerical oriented topic. Here is question number 13. Let's read the question first. A hydrogen-like species, that is important, with atomic number Z is in a higher excited state N and emits photons of energy 25.7 electron volt and 8.7 electron volt respectively to make transitions to the first and second excited states. Determine the value of N. What is N? N is a higher excited state, higher than the first and the second excited states. So we have to ponder over many data given in the question. Hydrogen-like species which contain one electron like hydrogen atom. Now, the energies are given in terms of electron volt. Now, you have learned energies in terms of electron volt, kilojoules per electron volt, kilojoules per mole, and joules per atom. Correct? And here, this formula involves ionization energy. So, you have learned ionization energy of hydrogen atom in terms of joules. What is that? 2.18 into 10 to the power of minus 18 joules per atom. In terms of electron volt, it is 13.62 electron volt. This is the value that you have to use in this calculation. And then in terms of kilojoules per mole, it is 1312 kilojoules per mole. These numbers, I've just made a list of these values, not that all of them are going to be used. You're going to use only the second value in terms of electron volt. But the display of the representations of these numbers will give you a quick recollection, because this chapter is full of a lot of numericals and a lot of formulae and numbers that you have to remember. All right? So which formula should we use here? Energy is equal to the ionization energy of the hydrogen-like species, okay, into 1 by N1 square minus 1 by N2 square. So N1 is the original level. The electron jumped to the higher excited state, that is the final excited state, and came back to the lower excited state. All right. So this is an emission spectrum. You remember that, correct? So this can be further written as the ionization energy of hydrogen-like species is equal to the ionization energy of hydrogen atom into the square of the atomic number into 1 by N1 square minus 1 by N2 square. Okay. Now, there are two energy levels. So this is your ground state. We will simplify this further. But before that, let's understand this. This is the ground state, right? The ground state is nothing but N is equal to 1. Then comes N is equal to 2, and then comes N is equal to 3. You are aware that the energy difference between subsequent energy levels goes on decreasing as the energy levels, as the distance from the nucleus increases, right? So this will be the first excited state, and this will be the second excited state. All right. So we have to substitute n is equal to 2 for the first excited state and n is equal to 3 for the second excited state. All right. So let's substitute the values. So the energy is given as 25.7. That is equal to, the ionization energy has to be written in terms of electron volt, 13.62 into Z square into 1 by 2 square minus 1 by n square. N is equal to 2 being the first excited state. So that is equal to 13.62 into Z square into n square minus 4 divided by 4n square, that is 25.7. So let's call this as equation number 1. All right. So here we have 8.7 is equal to 13.62 into z square into the second excited state would be 1 by 3 square minus 1 by n square, which is equal to 13.62 into z square into n square minus 9 divided by 3 square is 9, 9n square, and therefore this is equation 2. Now let's divide equation 1 by equation 2. Okay, so equation 1 divided by equation 2. Right? So what was equation 1? Equation 1 was 25.7 divided by equation 2 was 8.7. 13.62 into z square will get cancelled eventually. 13.62 into z square. And now the next calculation is, the next substitution is, you had n square minus 4 divided by 4n square divided by n square minus 9 by 9n square. Okay. Now what is so 25.7 by 8.7? We can do a small approximation as 26. So I'm writing the value here. This can be 26 and this can be 8. Sorry, 9. This can be 9. 8.7 can be rounded off to 9. So 26 by 9 is approximately 3, 2.9 something. So let this be 3. We cancel these. 3 is equal to n square minus 4. The n square here gets cancelled into 9. The 9 comes up divided by n square minus 9 into 4. So I again transpose further. I get 12 by 9 is equal to n square minus 4 divided by n square minus 9. We can do all this quickly. When you're equating the two equations, you don't have to write these two factors. And you can also immediately divide, round off 25.7 to 26, then this to 9, and you get the value as 3 or 2.9. So all that can be done very quickly. Here I'm just trying to help you to understand the steps. Okay, and once you understand this, you'll be in a position to skip a few steps and arrive at the final answer faster. All right, so this is equal to 12 by 9 is again approximately 1.3. So now you have to use a trial and error method. You have to substitute n by. Your task is to find out n. So what will you substitute? Where will you start substituting? From which number will you start substituting? N should be greater than the first and the second excited states. The first excited state was 2 and the second excited state was 3. So let's start from n is equal to 4. Okay, so if n is equal to 4, if n is equal to 4, n square minus 4. What is n square minus 4? 16 minus 4 divided by 16 minus 9. So that would be 12 divided by 7, which is not equal to 1.3. Okay, so now what do we do? Next, we substitute as equal to 5. Sorry, n as equal to 5, the next value, right? So n square, 25 minus 4 divided by 25 minus 9. Now 25 minus 4 would be 21. 25 minus 9 would be 16. Now this is approximately equal to 1.3, and therefore the higher excited state is found to be n is equal to 5. So this is how you solve this question. We are on question number 14 now. Very simple question, but you need to be conceptually clear about quantum numbers to understand this question and answer correctly, because you have options which can confuse you. All right. So let's understand the question. What is the maximum number of electrons that can be accommodated in an atom in which the highest principal quantum number is 4? Four options have been provided. So one of the four options would be the right answer, and this type of question will appear in section A of your JEE exam paper. All right. So let's start discussing this question. So you need to find out the maximum number of electrons which can be accommodated in an atom whose highest principal quantum number is 4. Okay, principal quantum number would mean n is equal to 4. Let's start with n is equal to 1. All right, so all those orbitals are getting filled. Orbitals of the first energy level, orbitals of n is equal to 2, n is equal to 3, and 4. Right? So all those are getting filled till you reach the fourth period. So let's start with n is equal to 1. Right? So how many orbitals are there in n is equal to 1? Only one orbital, 1s. And you have how many electrons? So let me just write this. 1 second. Yeah. So let me write n orbitals and electrons. Okay. First n is equal to 1. Let me use a different color. First n is equal to 1. The orbitals are 1s, only 1s orbital, and there are 2 electrons which can be accommodated in the 1s orbital. Right? Next comes, so n is equal to 1 implies period number 1. First period, right? You have 2 elements in the first period. Then comes period number 2, so n is equal to 2. Now, what are the orbitals in period number 2, or n is equal to 2? In n is equal to 2, you have 2s. 2s, you have only one orbital, so 2 electrons. 2p. 2p has got 3 orbitals, right? 2px, 2py, and 2pz. So 6 electrons. 2 electrons in each of these orbitals. Now we move on to the third period. Okay, third, n is equal to 3, third period. So what are the various orbitals there? 3s, where 2 electrons are accommodated, 3p, which is 3px, 3py, and 3pz. 6 electrons are accommodated. You have to add up all these electrons, okay? All these electrons have to be added up to get us the final answer. Now we move on to, let me use a different color for n is equal to 4. When we say n is equal to 4, we mean the period in which, the row of elements in which the highest principal quantum number is 4. It cannot exceed 4. So think about the fourth period. The first 2 elements are present in 4s orbital, 4s1, 4s2. So 2 electrons in 4s, right? And then you have 4p, which is 4px, 4py, and 4pz, and there are 6 electrons. But between 4s and 4p, you have 3d orbitals. There are 5 3d orbitals. You know the 5 3d orbitals, and therefore 10 electrons can be accommodated in each of those 5 3d orbitals. Okay, so we stop there. At this point, we stop because in the fourth period, you start with 4s, then you have 10 3D elements, and then you have 6 4p elements. We are done with the fourth period. Although you know that when n is equal to 4, you can also have orbitals which are 4d and 4f. But we have to stop at 4p because 4d and 4f come in subsequent or by subsequent periods. 4d comes in the fifth period, correct? And 4f comes in the sixth period, but not in period number 4. And in fifth period, the highest principal quantum number is 5. In the sixth period, highest principal quantum number is 6. So we have to exclude 4d and 4f. I have a reason for saying this. I'll come to that very soon. Now let's add all these electrons. If you add all these electrons, you have 4. You have got 4 plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, 30, and you have the final answer, 36. So this is the correct answer. Now, which are the answers given the given options which can confuse you? You have also learned a formula as 2n square, right? 2n square as the number of electrons in each shell or energy level. So if you substitute n as equal to 4, 2 into 4 square becomes 32. So 32 is also an option, but in this context, 32 is not the correct answer. We want 36. Okay, so this is the conceptual discussion of arriving at the answer 36. If you are thorough with the periodic table, you know that at the end of each period, you have the noble gas. So you have helium with atomic number 2, right? Followed by neon, 10. Second period is neon. So I'll just write the noble gases here. So what are the group 18 elements or the noble gas elements? You have helium here with atomic number 2. You have got, in the second period, you have got neon with atomic number 10, right? So helium, neon, and then you have got in the third period, you have got argon with atomic number 18. After argon in the fourth period, you've got krypton with atomic number 36. So if you're able to recollect the noble gas present at the end of the fourth period, which is 36, will be the right answer. Okay, so there is a shortcut way of getting the answer 36. All right, but this is the conceptual way to understand how you get the answer 36 as your final answer, and therefore option D is the correct answer. If you found today's video useful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is given in the description below. See you tomorrow.